All right, let's get into it. We're on the internet all day, every day, but what's really going on behind the scenes? In this explainer, we're going to follow the invisible, ridiculously fast journey that just one little piece of your data takes every single time you go online.
I mean, really think about it. You click something, a video, a link, whatever, and bam, it's just there. But that split second, it isn't empty space. It's actually packed with this incredibly complex, perfectly timed dance of technology. And the star of our show is this little thing called a packet. That's the technical name for the tiny bundle of data that's carrying your request. We're going to follow just one of these packets from your keyboard out into the wild world of the internet and all the way back home.
So the whole adventure kicks off right inside your web browser. When you click, the first thing your browser has to do is look up the website's address. Think of it like a super fast search in the internet's phone book, which is called DNS. Once it has the address, it creates a request, using a very specific language to ask the server for the web page. This is called an HTTP request, and it basically just says, hey, can you please send me this file?
But how do all these different computers and servers and phones actually talk to each other? Well, they use protocols. You can think of protocols as the official languages of the internet. You know, just like people need a shared language to have a conversation, computers need these super strict rules to make sure they can exchange information perfectly, without any mistakes.
Okay, so we've got our request. But a whole web page? That's way too big to send in one huge chunk. What happens if a piece of it gets lost along the way, or if it all shows up in the wrong order? Yeah, that would be a mess. The internet needs a system to make sure everything gets there in one piece.
And that system is called TCP, or Transmission Control Protocol. What TCP does is brilliant. It takes your big request, chops it up into smaller, easy-to-manage packets, and then it numbers every single one. It's kind of like writing a really long letter but on a bunch of numbered postcards. That way, even if the mailman delivers them out of order, the person on the other end can easily put them back together correctly. Now, before a single packet is sent, TCP does this lightning-fast three-step handshake. First, your computer sends a message saying, hey, I'd like to connect. The server on the other end replies, got it, I'm ready for you. And then your computer says, awesome, the connection is open. It's this digital ready, set, go, using signals called SYN and ACK that make sure both sides are totally ready to communicate. So how does our little packet get all its travel instructions? It happens through a process called encapsulation. And honestly, the best way to picture this is to imagine putting a letter inside a series of envelopes. With each step of the journey, we're going to add a new wrapper, a new envelope, with very specific information on it.
Right at the very core, in the very first envelope, is the payload. This is your actual web request. This is the original message, the what, that we need to send.
Okay, the first wrapper we add is the TCP header. This contains those sequence numbers we just talked about, so we can reassemble the message. But it also has something really important called a port number. The port number tells the computer on the other end exactly which application should get this packet. In our case, it's telling it, hey, deliver this to the web browser.
All right, our packet is now packed up and ready for reliable delivery to the right application. But where in the world is it supposed to go? It needs a long-distance address, a global address.
And that is the IP address. Every single device connected to the internet has one. But here's the cool part. Unlike a permanent physical address, an IP address is logical. It's more about where the device is right now on the network. This is the packet's ultimate cross-country destination address. So the very next wrapper that gets added is the IP header. And this one is simple but crucial. It contains just two things: the IP address of your computer, the source, and the IP address of the web server, the destination. Now our packet knows exactly where in the world it's going.
So the packet knows its final global destination. But the journey doesn't just start by teleporting across the world. No. The very first step is actually a really short one. It's just getting from your computer to your local router, which is probably sitting just a few feet away from you right now.
And to make that tiny little jump, we need a totally different kind of address, a MAC address. If the IP address is like your home's postal address for global mail, the MAC address is like a unique permanent fingerprint for your device's network card. It's only used for delivering the packet to the very next device in the chain, and that's it.
So we add the final wrapper. This is the data link or Ethernet header. This last layer contains the MAC address of your home router. And with that, our packet is fully dressed and ready for the very first hop of its big adventure.
And at this moment, something amazing happens.
Our fully addressed packet stops being just abstract data. It becomes a real physical signal. It could be a flash of light pulsing down a fiber optic cable, an electrical signal zipping through an Ethernet cord, or it could be riding the invisible radio waves of your Wi-Fi. So once our packet hits your router, it's officially on the internet, this mind-bogglingly huge network of interconnected networks. Now it has to figure out how to navigate this massive web, and that process is called routing.
You can think of routers as the traffic cops of the internet. Every router has something called a routing table, which is basically a simple cheat sheet of directions. When our packet arrives, the router just looks at its destination IP address, checks its table and goes, to get to that network, you need to go this way. Then it forwards it to the next router. This happens over and over, hop after hop, getting a little closer each time, all within microseconds.
After jumping across maybe dozens of routers, all in less than the blink of an eye, our packet finally arrives at the destination server. Whew! But guess what? Its job is only half done.
This server now does the exact opposite of what your computer did. It starts unwrapping each of those layers one by one. It reads the Ethernet header, then the IP header to make sure it's the right place, then the TCP header to know which app to give it to, until finally it gets to the original data at the center, your HTTP request.
And now, the server gets to work on the response. It grabs the web page data you asked for, breaks that into brand new packets, and wraps them up in the exact same way, with TCP, IP, and Ethernet headers. These new packets then start their own high-speed journey all the way across the internet, back to you.
So you see, when we talk about the cloud, it's not some fluffy, magical thing in the sky. The internet only works because millions and millions of devices all across the entire planet have agreed to follow the exact same set of rules, the same protocols for how to pack, address, and move data. It is a truly stunning achievement of global cooperation.
This whole incredible system is built on agreement. And as our technology keeps connecting us in new and even more powerful ways, it really makes you wonder, right? What are the new rules, the new protocols that we're going to need to invent to navigate the future? What's the next great global standard we'll all need to build together